to lesson 19, and today what we're looking at is absolute values. And we want to look at solving absolute value equations and inequalities. I thought it was kind of a nice thing to put together and look at it all at once. Now, I've given you a definition here of what an absolute value would be, and I really think it helps to use this definition a lot of the time along the way in our work here today. I said it's the distance that x is from the origin on the number line. I know, you might say, that's not how I recall it. You might say, I recall that essentially it wipes away any negatives. So the absolute value of -5 is 5, and the absolute value of 4 is 4. Okay, well, you're right. That's how we can work with it and do some computations with it. But I think as you work with these inequalities and equations, it's a good idea if you have a little bit stronger feel for it. Meaning this, on your number line, you can go either direction. You can go left or you can go right, okay? And so this is saying the absolute value of -5, well, that happens to be 5 units away. Now, yes, it's to the left, but I gave you a little note here. Since I defined this to be distance, distance is always a positive quantity. So the absolute value of -5 is 5. In the case of a +4, well, here sits the 4. How far is he away from 0? Well, he's 4 units, and that's why his absolute value is 4. All right? So I think, you know, it's a good idea if you try to switch your thinking into this definition. Now, we're going to start out with some real easy ones, like, I guess I like 5 today. Absolute value of x is equal to 5. And we'd like to solve that. Well, we go to our number line and we say, what is 5 units away from 0? Here's my 0. Well, 1, 2, 3, 4, 5. I can go 5 left, or 1, 2, 3, 4, 5. I can go 5 to the right. All right, so essentially, I have got 2 answers. X can be 5, or x can be -5. Now, by the way, I decided to give you another way of looking at this problem and the next couple that are related to this. What I've put up here is the graph of y equals absolute value of x. Remember back when we did our library of functions and then we did transformations? We graphed that absolute value to be the v. Okay, so the blue graph here is the absolute value of x. Okay? And then I put another line going across that of y equals 5. So in essence, our solutions are where these two graphs intersect. And they're intersecting at -5 and at 5. Okay? It's just another way of looking at it, and what's kind of nice from a geometry teacher's standpoint. Here's my one-dimensional view, and here's my two-dimensional view. All right? Now, if we continue on, I'd like to know for what numbers x will the absolute value of x be greater than 5? Now remember what absolute value means. Absolute value means its distance away from 0 on the number line. So here's my 0, and I need their distance away to be greater than 5. Okay, well then I could certainly go to 6 and 7 and 8 and all those guys, but I could also go to 5.1, couldn't I? And 5.2. So I put an open circle on 5. Do you know why I have to put an open circle on 5? Well, because 5 isn't farther than 5. So I put the open circle and anything to the right. All of those numbers are farther than 5 units away from the origin. Now that's, of course, going in the right direction. Go on the other side. Here's my negative 5. Well, I can't use the negative 5, but I can take any number to the left because all of those numbers are farther away. Now, if we look at the two-dimensional picture, here's my absolute value of x. Here's where it's equal to 5. So where will the x numbers be so that the absolute value, the output, is bigger than 5? Well, that's going to be all of this and all of this. All of these are greater than 5. And if you think of kind of smushing this down onto the x-axis, I had a colleague say that today, and I thought it sounded like a lovely idea. If you kind of smash that down, you end up with your x values going from positive 5 to the right, negative 5 to the left. Just another way of looking at the very same problem. Okay? Now, by the way, another way we can write this is certainly with the nice little inequalities. X is greater than 5 is this one, and x is less than negative 5 is over here on the left. And my connecting word is or. These two things cannot happen simultaneously. So essentially, it's I can take any number bigger than 5, and that will be a solution, or I can take any number less than negative 5, and that would be a solution as well. All right? Well, what about the last option? By the way, we have a trichotomy property in the real numbers that says either these two numbers are equal to each other, or this guy's bigger, or this guy's bigger. 3 possibilities. And so here's our third possibility. My absolute value is less than 5. So let's look at that. Here's my 0 on the number line. So I'm concerned with who is within 5 units of that. Well, certainly all of these numbers close to the 0 are within 5 units. So I can go from negative 5 up to positive 5. Any of those numbers are within 5 units. Right? Their distance away from 0 is less than 5. Now, on the graph, here's my nice little v for the absolute value. Here's where it equals 5. Now, where am I getting numbers smaller than 5 out of my absolute value? Well, that's all of these numbers going down to the point of the v. And if you think of collapsing that down onto the x-axis, you can see in another way that we're running between negative 5 and 5. Hey, and did you catch there was this little bitty word I just said? I said they're between negative 5 and 5. Now, I know that in math sometimes you get so frustrated with words. In logic, the word and the word or have very important meanings, and they change things. In this particular case, I have to have both of these numbers true. Now, here's why. If you simply take numbers less than 5 or greater than negative 5, I could take a number, say, negative 10, because that would be less than 5. But if you put negative 10 into there, I don't get a solution. These two things have to simultaneously happen. It has to be smaller than 5 and has to also be bigger than negative 5, which, by the way, this picture is showing. All right? So we do change the word in there. Now, another way of writing that is in a 3-part inequality. And I don't know how much experience you've had with this in the past. There's different ways of reading this. You can start in the middle, read left I know, we're not used to that, sorry. And then read right. You can say x is greater than negative 5 and x is less than 5. That is one proper way to say that. But you know the easiest way to say it? X is between negative 5 and 5. And I like that notation because it is exactly like it looks. The x numbers I'm looking for are between negative 5 and 5. Okay? One last thing I want to tell you about this three-part. Anytime you have a three-parter, you want to kind of read all the way through and see if it makes any sense. And here's what I mean. Negative 5 is less than 5. It does make sense as you read through that. And here's what I mean. It would be very strange if you had negative 5 is less than something which is greater than 5. And you look at that and say, well, that just doesn't make any sense at all. So whenever you're using 2 in a string, they generally are going to have to run in the same direction. And try to read through that and see if what you're writing makes any sense at all. Okay? Now, how do we use our number line in order to solve these as they get more complicated? So we've got absolute value of 3x plus 5 is equal to 8. Okay, now, I know you have experience with solving equations. You know I'm going to subtract that 5, and you know I'm going to divide that 3 off. I am, but not yet. Why? Because the 3 and the 5 are in the bars. It's like they're in prison, okay? They are behind the prison bars and you can't touch them. I have seen students do all kinds of crazy things with their absolute values. Think of it as those bars are keeping you from touching them. So the first thing you have to do is remove the bars. Then everybody can go, all right? Now, how do we remove that? Well, we look at what it says. This absolute value is equal to 8. Now, that means the argument is the part inside here, this 3x plus 5. Well, he's either 8 or he's negative 8. Why? Because those are the two that happen to be, the two numbers that happen to be exactly 8 units away from 0. So here's what I can say. I can say, all right, 3x plus 5 equals 8, or, these aren't happening simultaneously, 3x plus 5 equals negative 8. And now that the bars are no longer there to prohibit me from moving these terms, I'm ready to go. Subtract that 5 off. 3x is equal to 3. X equals 1. Or subtract the 5. 3x equals negative 13. X equals negative 13 thirds. Are you surprised that there be 2 answers on an absolute value? Well, probably not if you remember the idea of having the V shape on it. And so if I'm cutting across there, there's a very high likelihood that I would get 2 distinct results. And how could I check them? Well, I can put them back. If you put in the 1, we get 3 plus 5, which is 8. Absolute value is 8. Put in the negative 13 over 3. I know it looks scary, but it's not. 3 times this cancels the 3 out, and we get negative 13 plus 5. There's your negative 8. Yeah, I have 2 solutions. Well, now we're going to continue to play this. Not every time, but now I'd like to know, okay, where's 3x plus 5, the absolute value of that, greater than or equal to 8? Now, I'm putting the number lines on here in the beginning You don't have to use the number lines, but I kind of like to use them sometimes in helping me think about setting up the problem. Because you can see if I need my distance from 0 to be 8 or bigger, I'm going to be at -8 left, or I'm at +8 to the right. And then what it allows me to do is to write my two statements. From here, 3x plus 5 is less than or equal to -8, or from this branch, 3x plus 5 is greater than or equal to +8. You see, now the bars are removed, so the 5 and the 3 are free pickings. I can go at it. Now, do remember that there's a little bit of variation on your rules on solving inequalities. The less thans, the greater thans, they change if you multiply or divide by a negative. Otherwise, they're exactly the same as working with your equations. So, subtract my 5 off. 3x is less than or equal to -13. X is less than or equal to -13 over 3. Or, from here, 3x is greater than or equal to 3. X is greater than or equal to 1. Now, sometimes you want to write that answer in interval notation. So this is where I'm less than -13, so it could go way out to the left, -infinity, up to -13 over 3, close it. Hey, if you'd like to call that -4 1/3, go for it. Union, 1 and bigger, would be 1 all the way up to +infinity. And I have infinitely many answers to that particular inequality. By the way, I also have infinitely many non-answers. Pick anything in between here, that's not going to work well. All right, last guy. For the moment, we're going to consider what if he's less than or equal to 8? Well, that means that he would be at -8, +8, and anything in between. Isn't that where the distance would be less than or equal to 8? Now you see, that's where I like to look at this, because then I immediately say, oh, then 3x plus 5 is going to be between -8 and 8. I like that notation. Hey, by the way, what's kind of cool about it, if it saved everything from before, notice that when I have one segment, I can get by with one inequality statement. Okay? And it's kind of cool. I've got two ends. I have two ends in the middle there. Okay? Back here, notice that I have two separate segments. And in that case, I have to have two separate inequalities that I work with. So it's really kind of neat. I love having that number line to kind of organize my thinking process. Okay? So, if you've never worked with this before, it's kind of like, sometimes I'll pull up three students and talk about their height. I'll put them in order by height. So let's just pretend for a moment, I guess we can do it over here. Let's pretend that we've got a shorter person, middle person, and a taller person. I'm quite the artist, right? Okay, we'll just call them A, B, and C because I don't want to take time to write big names out. Okay, now what happens if they all grow 3 inches? Because right now you realize that height-wise, just talking about height-wise, we could set up that inequality. And if they all grow 3 inches, so if their height goes up by 3, do you realize they're going to stay in that arrangement? This guy's still going to be the shortest, and this guy's still going to be the tallest. Okay. What if they shrink by 2 inches? They're still in the same arrangement, right? Okay. Well, what if I cut them in half? I know, that's a weird idea. But if I cut them in half, it still is going to stay in this very same arrangement. Okay, what if they all double in height? Stays in the very same arrangement. Of course, that is dependent upon you doing the same operation to all 3 parts. See, you're used to, on an equation, having a left side and a right side. Well, now you got to consider you've got a left, a right, and a middle. Okay? Meaning this. I've decided that I want to subtract 5 in order to solve this. And that is totally legal as long as I subtract 5 from each of the 3 sections. Because as long as I do that, this inequality is going to be maintained. Okay? So that gives me negative 13 is less than or equal to 3x is less than or equal to 3. And then, to get the x by itself, I want to divide by 3. That is totally legal as long as I do it to each of the 3 sections. And since I'm dividing by a positive 3, I do not change those inequalities. And so I get negative 13 thirds is less than or equal to x is less than or equal to 1. And if I'm going to write that in interval notation, by the way, that would be x is in the interval. My students always say, do I have to write that? Most instructors won't make you write that, okay? But it'll be in the interval that's closed on the left from negative 13 up to 1, and it's closed on the right. Okay? Well, you know what? That's about it. So now we just need to practice a few and get a better feel for it. Okay? This big old nasty ugly absolute value is less than or equal to 6. Well, that means that it has to be falling between negative 6 and 6 on the number line. Because that's how I have the distance less than 6. You see one segment? Okay, so that means do 3x minus 3. Oh, I think I like the black maybe a little better here. 3x minus 3 over 4 has to be between negative 6 and 6. Yeah? One segment, one statement, 2 endpoints. To solve this guy, I'm going to multiply through by a positive 4, so I do not change the inequalities. And I get negative 24 is less than or equal to 3x minus 3 is less than or equal to positive 24. That I need to? We know you're trying to get x by itself, so you want to look right here in the middle where the x is located. This minus 3 is the guy I want to get rid of now. So I add 3 everywhere. That gives me negative 21 less than or equal to 3x less than or equal to 27. Last thing, divide by that 3. And a positive 3, so keep it. Negative 7 is less than or equal to x is less than or equal to 9. And if you want the interval notation, then x is an element of the closed interval from negative 7 up to 9. And you know you can check this. How could you check it? I don't love to check these, but you know sometimes it's important. You can try the negative 7 and the 9 in. They should hit it at exactly 6 because they're my endpoints. And then you could take a number between negative 7 and 9. 0 would be convenient. And put it in, and you should find something less than 6. Okay? And then if you want to be an overachiever, you could try something outside the interval and show that it doesn't work. Okay? Well, what's different? Well, the 2 and the 1 are inside of the jail or the prison, okay? You cannot touch that. But that 3 is hanging on the outside. What should you do? Get rid of him right now, okay? What you want to do is get that absolute value guy by himself before you try to come out of the bars, all right? So what we need to do is divide the 3 off. Absolute value of 2x minus 1 is equal to, notice we do not have an inequality here, is equal to 7. Now I have only an absolute value over here, and if you like, you are not required to, but you can make your own number lines. I could say, okay, here's negative 7 and 7. If I'm going to be exactly a distance of 7 away on the number line, I have to be sitting at one of those locations. So 2x minus 1 is equal to negative 7, or, and that is the correct connecting word here, 2x minus 1 is equal to positive 7. Once you come out of the bars, you are ready to solve. It becomes 2x is equal to negative 6, x is negative 3, or x is 4. Okay? And I wouldn't write that in interval notation. Wow, I got all kinds of junk now. And as I look at all this junk, I'm thinking, okay, I need to get that absolute value guy by himself. So what am I going to move first? I'm going to get rid of that 4. Okay, subtracting the 4 gives me negative 3. Absolute value is greater than or equal to negative 27. Now, I need to divide off this negative 3 because he is outside the absolute value. So, I divide both sides by negative 3. And when I do that, remember, because he's negative, I have to change that inequality sign. Okay? And that would give me then a positive 9 over there. Now that I have the absolute value isolated all by himself, now I can deal with that problem and say, okay, well, if the absolute value has to be less than or equal to 9, that means it has to be sitting between negative 9 and positive 9. Ooh, I have one segment, don't I? That's one of those between situations. The numbers I'm looking for are between negative 9 and 9. And now it's easy. Subtract 7. Negative 16 is less than or equal to x, less than or equal to 2. And there's infinitely many answers. That's when it's a nice idea to use that interval notation. So x is an element of negative 16 up to 2, closed on both ends. Okay? Well, this looks a lot like the last guy. All right, let's move the 27. Okay, we get 5 absolute value is equal to negative 5. Now, you know, you might be thinking at this point in time, this is a little bit weird, isn't it? Or maybe it hasn't dawned on you yet. I could divide the 5 off. Of course, that didn't help the problem, did it? You know what the problem is? how can my absolute value be equal to a negative number? It can't, can it? Which means there's no solution to that. Because in order for this to be true, my absolute value would have to be equal to a negative number. And you know distance can only be given as a positive quantity, so there's no solution on that. So watch, every once in a while as you're working with your absolute values, if that negative pops up, first thing to do is to make sure you have not made a mistake up to that point. But if you have not made a mistake, there's no solution. Okay, so just a quick recap. These weren't so bad, were they? To solve equations and inequalities that have those absolute values, I do want you to use an algebraic process. Because you know, sometimes we've used some graphical kinds of things, although I do think the number line helps. I suggest that you first isolate that absolute value portion, then set up your inequality. Okay? And I said sometimes that inequality is a three-part inequality and sometimes it is two separate. And if you kind of do a rough sketch on the number line, you'll know which one you're looking at. And then you solve each of those statements individually. Okay? But of course you've got to remember you cannot solve your problems in the bars. There's a thought for your life. Nothing can be moved into or outside of those bars. Now, technically, if you really know what you're doing, we do have some theorems that allow you to do some of that work. But we're not going there at this point in time, so please heed my cautions. Don't move anything inside or out of those absolute value bars. Remove the bars first. Then go for the solving. Okay? Practice those, have fun, and I'll see you in the next lesson.